My name's James. I'm a technology principal at ThoughtWorks. I've been with ThoughtWorks about 8 years. I guess my job description is kind of a coding architect. So what do I kind of mean by that? Well, I spend about sort of 80% of my time probably writing code. So hands-on on projects, writing code. I've been working in C# most recently, but before that, I guess most of my experiences have been in Java. My speciality really over the last decade have been sort of enterprise integration, integrating systems, building out service-oriented architectures, that kind of thing. And that's kind of led me to be very interested in this topic tonight, which is microservices, with the subtitle, Adaptive Systems for Innovative Organizations. You can kind of think of this, I think, as, well, for me, it's almost like the London School of Architecture, in the same way that there's kind of a London School of Test-Driven Development. There's a kind of London School of Architecture. So you'll probably be hearing me refer to quite a few other people during the course of tonight, former colleagues of ours and clients that we've worked with who have really sort of driven the agenda on this topic of microservices. So the talk is in, I guess, 2 parts or so, maybe 3 parts with a conclusion. The first is a look at some of the challenges facing us at the moment, facing our organizations as we move into the brave new world of the Internet of Things and the web becomes a dominant force for most of our businesses. Then I'll talk through the characteristics of microservices. So, microservices are building systems out of small components that are communicating with one another, sort of distributed systems, building applications out of distributed systems as distributed systems. But there's a lot of stuff that goes behind that. There's a lot of kind of plumbing glue that makes the architectural style of microsystems kind of work. So I'll be covering off a whole bunch of different characteristics that we've sort of come to sort of, I guess, believe are kind of essential if you're going to be building distributed systems out of microservices. Okay, so I guess the first thing we're going to talk about is the world it's a-changing, or why you should be afraid, very afraid. So it's quite scary, actually, the kind of symptoms that we see looking around in big organizations and governmental organizations, the way we actually design and build systems and have done for the last sort of 20 years. Here's an example of this. We waste huge amounts of money, huge amounts of money. I think this is from an NHS project that failed, £12.7 billion worth of taxpayers' money that was wasted on a failed IT implementation. Now this kind of sucks, right? This kind of sucks because this is our money, we pay taxes, and this is £12.7 billion worth of our money that's kind of gone down the drain. There's another kind of symptom is that we have to sort of rebuild our applications every sort of 2 to 5 years. People are probably familiar with this kind of cycle. You kind of build something, it's going to last forever, but it suddenly becomes kind of big and kind of complex and difficult to change, and so you have to go back to your CFO and you have to say, do you know what? We need another 10 million, we need to rebuild it again. That kind of sucks. Here's a statistic for you. So apparently, according to Gartner, 90% of the total cost of ownership of our systems is incurred post-launch. So if you spend 10 million building something, you're going to be spending a lot more than that over its lifetime. And if that lifetime is only 2 to 5 years, then that's a lot of money to be spending. At the same time, the web is kind of changing the way our businesses work. There's a great story. I think one of my favorite client stories, I wasn't in the room, but one of my colleagues, Ian Cartwright, tells this story. He was at a big music retailer, bricks and mortar music retailer some years ago. And there was talk about digital presence, we should be selling music online. And the CTO of this bricks and mortar music retailer, he sort of turned to Ian, he said, well, I don't think there's anything in this World Wide Web business, this internet business. It'll blow over in 5 years and we'll be back to selling music in the shops. Yeah, how very wrong they were. It's not going away, and it's changing the way we work at the most fundamental level. And if you think about Amazon, how they've changed the face of retail, and as a knock-on effect of that, have actually invented pretty much an entire new industry, which is cloud computing, utility computing in the cloud. We also kind of build these systems that are massive, big monolithic things, right? So we build systems that are composed of giant bits. They're not decomposed. We've come up with entire disciplines to help us manage the complexity of building building big systems, things like domain-driven design. We've had to come up with entire kind of categories, see things like entities, value objects, aggregate roots, all these different things that we've had to sort of invent in order to make some sense out of these big monolithic applications that we're building. That's kind of scary. And they become very, very difficult to change, in my experience. One of the things we often see at our clients is, in ThoughtWorks, is we do lots of things like organizational assessments or architectural assessments. And you talk to business folks on the other side of the yawning crevasse of doom from IT, you talk to business folk, and one of their main concerns is, why does it take so long to make a change? I want to make a very, very simple change, but it takes 6 months to get it done. It's kind of, and that's a real concern to people. We end up with these systems that are composed of sort of big balls of mud, kind of big like spaghetti code bases, where change becomes really, really hard. Also, in sort of big organizations, the kind of big enterprises, you often get this problem where things take months and months to release. You have these release trains that, rather than taking hours or days or weeks of the being pretty long in itself, take months. I've been at a couple of places where you find out a very, very simple change, maybe even like adding a form field to a sort of online form will actually end up taking months, because it has to sit behind the release train of all the other features that are going in. And that kind of sucks, because at the same time, we're competing against an entirely new generation of entrepreneurs, right? Entrepreneurs who are kind of growing up around this idea of lean startup. There are books being written about this everywhere: lean startup, startup owner's manual, these business model generation, all these kinds of these techniques that are starting to have a real impact on how we run our businesses. And these kind of dudes who kind of in the kind of startup world, they're kind of web native. They're sort of virtualization, infrastructure as a service native. They're able to take advantage of the fact that we can now treat compute as effectively a utility. Gone are the days where we actually have to have our own data centers. We can actually use other people's data centers. Actually, people who are much better at running, dare I say it, data centers than we are. People like Amazon Web Services. Think of rack space organizations like that, who've got a huge amount of experience in doing this now. And gone are the days, hundreds of years ago, where we would generate our own electricity. You don't have like a CEO, which is like kind of chief electricity officer in your organization anymore. Whilst in the past you might have done, in the past you might have had to generate your own electricity. We don't do that anymore. We plug our boxes into the wall, into a socket, and it's done for us. All right? And this is kind of this is the world we're now living in. And even more scary, this new generation of entrepreneurs and these companies that are kind of web native and that are taking advantage of the net, they can kind of accidentally take us out of the market, right? This is a quote from Harvard Business Review, HBR. So the innovators who create products at hackathons aren't even trying to disrupt your business. You're just the collateral damage. And probably the best example I know of that is Apple. So people are probably familiar with the story of TomTom and what happened when Apple launched their iPhone. Apple weren't trying to wipe TomTom out, but TomTom actually lost, over the sort of course of a couple of weeks after the iPhone was launched, about 75% of their market value, accidentally, because the iPhone was launched with this mapping service on it. Apple weren't trying to wreck the business of TomTom. It just kind of happened accidentally. This is kind of a scary place to be. This is a scary world we live in if you're in a big organization that aren't used to these kind of ideas. So what are the things we can kind of do? Well, it's, as I say, it's quite scary. The dark clouds are gathering. I took this photo earlier. Quite scary. After all that, I've got this terrible hay fever. This is why I'm sounding a bit nasal. After this kind of like beautiful period of sunshine we've had, suddenly the dark clouds are gathering. But there are organizations who are taking advantage, who are able to take advantage of these changing circumstances, right? So anyone give me any examples of organizations that are kind of web native, are web ready, are successful in this new world in the audience? And that's a question. Netflix. Well, Netflix are a great example of that, and I'll have to give you the money I promised you afterwards, because that's my next slide actually. So Netflix are a fantastic example of an organization that have been able to affect a challenge bricks and mortar retailers, and they're now pretty much ubiquitous. How many people in the room have got a Netflix account? Put your hands up if you've got a Netflix account. Who's got a Love Film account? Yeah, so I've got both actually. I'm a sucker for punishment. Turns out they get newer stuff on Love Film, but I prefer the Netflix service. Netflix are a great example, and they're also an example of a company that are pioneering this new approach of building small services that are talking to other small services in a big distributed system. They've got about 350 odd microservices at Netflix. That was probably as of a month or so ago. They've probably got another 50 or so by now. And managing the complexity of that kind of service estate has been really driving a lot of what we're going to be talking about tonight. Another example, actually, is in the UK. I think we've probably got some representatives from here tonight. So anyone from GDS, from the Government Digital Service in? We've got one over there. Anyone else? Simon? So the Government Digital Service are doing some really, really exciting work. This is a sub-department in the Cabinet Office that was formed, I guess, 4 years ago, with a specific remit of ending the kind of awful kind of expenditure that government, the kind of mistakes that the government have been making in terms of IT expenditure and in terms of managing contracts with large suppliers. Effectively, they're bringing agile software development techniques into the heart of government, and in fact wield a veto pretty much over government department spending. And they're doing it from a really kind of interesting open source agile point of view. And actually some of the techniques I'll be talking about kind of form a key part actually of where they're trying to go. But there's an interesting thing here. Who'd have thought that number 10, make things open, make things better, would be a key component of the Government Digital Services design principles. All their code's available on GitHub. You can actually go to GitHub and actually look at the code that the government are producing, the developers in the government are producing. It's pretty exciting. And then you've got Twitter. Twitter, another example of an organization that have kind of been incredibly successful and also pioneered a lot of these techniques to do with having small, interconnected services talking to one another using simple protocols. So I guess to summarize, if we're to sort of survive, and I do honestly mean survive, as bricks and mortar organizations, or even traditional organizations like airlines or like insurers and specifically in this kind of new world, what are the sorts of things we want to do? Well, we want to be building systems that are cheap to replace. We want to be building systems that are quick to scale and that can withstand failure, and which crucially allow us to go as fast as possible. So to be able to develop features as fast as possible, but also to be able to pivot, to be able to switch direction, change direction, and avoid what Harvard Business Review calls big bang disruption caused by kind of startups that are effectively able to take our business away from us. So how do you do that? How do you start? Well, obviously the answer's in the title of the talk. You build microservices. But basically, what I think you do is you stand on the shoulders of giants. That's what you do. You try and absorb the lessons from the last sort of 2 decades or so, or even further back, 5 decades worth of software development, and then you turn it all up to 11. You put it all together. So whilst the talk is about building microservices, small interconnected systems composed of small services, the characteristics are really an exploration of stuff we've learned over the last several decades about how we build and design software systems that can allow us to move fast in the right direction. So the first thing I'm going to talk about is the idea of evolutionary design. Now, this is not a new topic. Martin Fowler wrote about this, I don't know, is it a decade ago now? There was a design is dead, I think. Or no, the new design or the new methodology, one of these topics. I always forget Martin's papers. But this is not a new idea, the idea of evolutionary design. I like to think of evolutionary design as composed of 2 different parts. The idea of evolutionary architecture on the one hand. So this is how we, at the macro level, build systems that are easy to flex and change and have enough degrees of freedom that we can change them as we go along. And then emergent design, on the other hand, which is allowing teams to make the right choices based on the circumstances they find themselves in. So emergent design being a kind of team-led thing, a developer-up approach, whereas evolutionary architecture is a bit more about the sort of the wider platform. I think we've been labouring, and this is not just me, a lot of people have been talking about this, that architecture is not like building a house. People have this kind of metaphor in their head. We need a blueprint. We have to specify everything up front. We need, like we're building a house. The difference is really, with a house, you can't have a house with 2 walls and a roof. Whereas with software, you can actually build things incrementally in different ways. The fundamental metaphor behind blueprints and building houses is kind of wrong. So I kind of prefer this metaphor. A colleague of mine, Eric Dunenberg, head of technology for ThoughtWorks Europe, came up with, I think, which is about town planning. So he talks about architecture as being more like, or building software is more like town planning and how towns evolve over time. So this is a screenshot from SimCity. There are probably some people in the audience, this is a very old version of SimCity, who are probably, this is probably older than some of the people in the room, which is fantastic. Not me, as you might have gathered, but probably some people. And this idea of evolutionary architecture is really about this kind of the idea of town planning and about how towns evolve. And I kind of think that evolutionary architecture, as opposed to design, so the architecture part, the thing that kind of, quote, architects are concerned with, are about the kind of the gaps between zones in a town plan. So if you imagine a town plan, you've got things like light residential, you've got heavy industrial zones, you've got all these different areas. You wouldn't put a power station in a light residential area, you'd put that into your heavy industrial zone along with all the factories and things. All right. So the idea behind town planning, or how towns evolve, is that the zones take on similar characteristics, similar things clump in similar areas. I kind of think that's a bit like how software sort of should work. We'll talk a bit about business capabilities and bounded context in a bit, but really these are kind of about bounded contexts. And evolutionary architecture is about the gaps. It's about the shared utilities between zones in your town plan. So, for example, it might be about the fact that we all share 240 volts DC in this metaphor. Or it might be about, it might be the fact that we all use the same language for our street signs. It's the stuff that's in between the zones. It's the stuff that links the zones together that's common. This example, I normally point at this. I can't really point. There's the red rectangle on here. I'm going to read it out because it's quite fantastic. It says, the power grid is almost divided in half. It's a warning in SimCity that tells you something. This is actually pretty much, in software, and when you build software, this is pretty much network partitioning. The network is about to partition, which is a fantastic kind of reference, I think. So evolutionary architecture is the stuff that's in the gaps, the utilities, whereas emergent design, which is the kind of the other side of this, the kind of developer up thing, you want to allow people to have as much freedom to choose implementations as possible, is within the zones. So how do teams build software out within the zones? How do teams build individual components of software out? That's kind of emergent design, and design that should evolve and emerge naturally over a period of time as teams are building the software. So I guess what I'm saying is, with evolutionary architecture, is that we should put in place just enough structure around our systems so that we can allow them to evolve, but the structure is fairly, there's some governance around what protocols we're using, how systems are talking to one another, what the shared utilities are, in the gaps between our business capabilities, between our software, between our systems, that within these capabilities, they should be allowed to evolve independently. And that might be in terms of technology choice, in terms of language choice, in terms of the patterns that are used. I've got this another colleague, Ian Cartwright. He talks about how he's really confused that at the start of a project, a greenfield project, you get your like really smart people together, and you get in a room and you try and think about exactly how you're going to put everything together. You do sequence diagrams, and you go down to the level of drawing out objects in UML diagrams and all this kind of stuff. And of course, it just goes in the drawer and everyone forgets it, and the software never ends up looking like the initial designs. And he talks about the fact that this is because we always try and decide how to build things at the point we know least about what we're going to build. If you think at the start of a project you know enough to design the entire system, you're kind of wrong, because it's the point you know least. Rather, we should put in place just enough structure to allow the software to evolve over a period of time, and trust the teams that are building out software, this is the emergent design part, to actually go out and build it. This is also a kind of you might have heard from Agile the idea of, or XP really, the idea of last responsible moment. When is the last responsible moment to take the decision about something? This is closely related. Often right at the start of a project, it's not the last responsible moment to take a lot of the decisions. We can defer decisions until we know more. So the next characteristic is this idea of business capability. So what is a business capability? So another colleague, Ian Robertson, he talks about a business capability, or capabilities, a set of interfaces at an endpoint that satisfy some kind of business goal. Right. Domain-driven design terms, it's kind of like a bounded context. A bounded context within which you have a ubiquitous language related to a specific thing. So I guess in the canonical example in the Blue Book, Eric Evans's Blue Book, they talk about shipping. They talk about shipping in containers. And they talk about the differences between different aspects, different objects within different bounded contexts within the domain of shipping. So you might have the kind of the billing system who's billing customers. You might have the scheduling system. They both need to know about containers because you need to know how much to charge a customer who's using a container, and you need to know how to route a container on the other hand. But they're kind of different bounded contexts. They have different aspects. They have different properties associated with them. That's kind of what this idea of a bounded context business capability is. And I want to talk about monoliths, as I said earlier. What we tend to do is we build systems that are composed of many bounded contexts all mashed up together. There might be many products, there might be many responsibilities of a specific of a specific domain. So you build a product that's got analytics and reporting and user management and billing all in the same place. And you end up doing things because we're developers, a lot of us, and we're smart people, and I do this all the time. You see abstractions, and you start thinking, right, so this thing over here looks a little bit similar to this thing over here. So what I'll do is I'll put them together, I'll create an abstraction, and often it's the wrong abstraction because you do it too early, and things become really, really hard to change, and you end up with this kind of big ball of mud, this big sort of spaghetti monolith over time. What we're saying in sort of microservices is, rather than end up with these big monoliths, what you do is you actually split these things out into separate processes. So rather than have all the different responsibilities running in the same process, you actually split them out so that they're running in separate processes. And crucially, as I've sort of indicated in the diagram, and this is the bit that gives a lot of people the heebie-jeebies, is you take the data with it. You take the data with the functionality. So you don't end up, in this case, with 4 separate processes all talking to the same database in a kind of spidery kind of mess with the database in the middle integrating everything. You actually take the database, you take the data associated with those services out to the side as well. And this can go to the extent that, well, with Netflix, for example, so Netflix did exactly this. They started off with a giant database, a big monolith. It became very, very difficult for them to change, for them to support the new features that they wanted to support over time. So what they ended up doing is splitting this out into many different processes, into these microservices. They called it fine-grained SOA originally. They're now talking about microservices as well. But they actually took it to the extreme where they split out every table separately. So when you look at their services, they're actually so fine-grained that it's a single operation on a single resource backed by effectively a single database table. And they've got, as I say, over 350 of these services that make up their system that produces that we know as Netflix. So that's what this kind of idea of a capability is. It's taking an individual piece of business functionality and splitting it out into a separate process with its own data. We also talk a bit about this idea of hexagonal architectures. Now, this is not new. This is from Alistair Cockburn I think at least 15 years ago, he talked about hexagonal architectures, about ports and adapters. And we'll talk a bit more about it in a minute. There is a reason why I've got hexagons around these examples, though. Crucially, and this is an example from a previous project I was on, when you take these capabilities out, they can be decomposed further, because often capabilities can be decomposed into one or more processes again. So you might not just have a single microservice that you break out, you might have more than one. But crucially, it's about decomposing based on your functional and cross-functional requirements. So it's not a case of How many services should we have, or how big should our services be? You should have a number of services dependent on the functional or cross-functional requirements that you have. So in this example, we've got 3 different processes, 3 different services. We've got 2 separate databases, and in this case, there was an event store fronted by an event queue. There was a number of competing consumers, and there was a user service in the background. And those 2 databases were actually different. One was a MySQL database, and one was a document store. So we're actually using different technologies, different storage technologies backing these individual services. But this was because we had the requirements around very, very spiky throughput. So we were going to have to support big batch loads overnight, and then kind of fairly run-of-the-mill CRUD operations during the day from websites. So we knew that we wanted to be able to scale processing of our requests coming in, depending on time of day and things. So we decided to use the competing consumer pattern to do that, fronted by a queue, and separated these things out. Now, if you were to do this in a single process, what you would normally do is use threads. No one said threads. I'm scared now. Is you would use threads, right? You might have a single thread that pops something into some kind of blocking queue, and then a number of threads off the back that are kind of reading things off that queue and processing them. In this case, actually, what we did is, rather than rely on threads, because personally I'm not smart enough to use threads, we actually separated these things out into separate processes that were managed independently from one another. Well, I talked about business capabilities, and I said sharing a uniform interface, because the thing is, when you start to tease things out into multiple processes, there's much more communication going on. Rather than making method calls, you're actually having to talk across the wire to other processes. So, like I said, sharing a uniform interface. What is that uniform interface? We'll be talking a bit about that in more detail. We've got this business capability. I said Alistair Cockburn came up with this idea of ports and adapters. So on the outside of these business capabilities, there should be a standard set of mechanisms that you can use to talk to these capabilities, that you can talk to the microservices. A standard set of ports, a standard set of adapters. Doesn't have to be one. Potentially it could be more than one, but you probably need to standardize on a specific set of them. And this is, again, back to the evolutionary architecture piece. This is the stuff that's hard to change afterwards. So you can standardize on simple standard protocols by which processes can talk to one another. There's lots of them out there. We'll talk a bit about that in a minute. So we had our example where our event queue was sort of fronting an event store with some competing consumers and things. What might we choose to actually front that as the standard protocol? So, talking with Martin Fowler recently, he came up with this idea of using rather than having dumb endpoints and smart pipes, which is kind of the business process modeling, or the kind of ESB model of building systems, of integrating systems. You have something with a lot of you put a lot of smarts into. We have this idea of having, rather than that, you have smart endpoints. The smarts live in the services, and you have dumb protocols between them. That's what we mean when we say smart endpoints and dumb pipes. And the thing is, standing on the shoulders of giants, we've learned a huge amount over the last couple of decades about how to get systems talking to one another. And there's been this evolution in integration over a long period. So going back to the example of data-oriented integration, this is basically databases talking to databases. And this goes back to late 60s, where we ended up with lots and lots of disconnected systems, stovepipe systems, which it was really difficult to get data into or out of. They weren't designed to get data into or out of. You might have heard the phrase swivel chair integration. This is a great kind of pointer towards stovepipe systems, where you've got one system that you have to log into, and you kind of do this, and then you have to swivel over to another green screen system to enter more data into. That's kind of swivel chair integration. But this is how systems were built a long time ago, and that's fine. The only way to get data between them generally was to do ETL, right? So you put a bunch of stuff underneath that copies from one database, stick it into another database, and that's data-oriented integration. Then you had sort of moved on to procedure-oriented integration. We all know probably about things like SOAP RPC, but I had the privilege and the pleasure of programming in like some Corba some time ago, and that was obviously, as I say, a delight. I also did some RMI, so that was obviously similarly a delight. And one of the key problems when you're doing RPC, when systems are talking together with RPCs, especially the old school kind of when you've got distributed objects, effectively, we just want to pretend that when we're invoking a method out of process in another location, it's the same as in process. You kind of forget there's a network in the way. And that tends to make a big difference when you're talking across a network. The characteristics of talking across a network, the problems you run into when you're talking across a network, are kind of not the same as when you're not talking across the network. What happens if the network goes away? So then you end up with lots of papers around things like the Byzantine generals protocols, where you have, okay, how do I put fault tolerance in so that I can invoke this, I can call this object across the wire. What happens if it goes away? Well, then maybe I'll use this, I'll put some kind of protocol in that will allow me to detect failure, but how do I detect? You end up with these kind of awful sets of conditions that you have to kind of, awful protocols that you have to program against. It becomes a nightmare. We then ended up with sort of document-oriented. This is kind of a step forward. I'm sort of clumping most of the kind of message-oriented integration techniques into document-oriented, because generally, we get a document, we stick it on the wire, it goes into some kind of message bus, we read it off. And finally, and I think this is where we are at the moment, this idea of resource-oriented programming, resource-oriented architectures, where we're bringing the web in-house. And I'll talk about that in a sec. So here's an example of data-oriented integration. This is a real example from a real organization. You don't really need to be able to read any of this. Effectively, all the dotted lines between things are ETL jobs. Right? So you've got a bunch of different systems, and you've got lots of dotted lines, and that's ETL jobs between all these different systems. It's pretty scary. I mentioned enterprise service buses. Well, this organization, they decided not to, because they'd obviously heard that enterprise service buses are a bit of a nightmare. ThoughtWorks have been preaching about this for quite a long time. I think Jim Weber calls them egregious spaghetti boxes, because what they do is they just hide. As an architect, it's brilliant because it makes all the squiggly lines on your diagram straight, because they all just go into this one box in the middle. Of course, it's all still squiggly inside. It's all still spaghetti inside. But that's by the by. Dan North calls them enterprise night buses. His theory being that generally you're drunk when you get on one. It doesn't take you where you want to go, and you get off covered in vomit. Now, if people have had experience with enterprise service buses, this has been my experience anyway. Apart from the drunk, I've never been drunk when I bought an ESB. What's brilliant about this diagram, you can't really see, but in the middle, there's something called, there's the three databases in the middle. That's actually called the middleware database. So rather than buy an ESB, we thought, wow, we won't buy an ESB, we'll just have a middleware database instead that everything goes into. It's a pretty extraordinary kind of thing. This is an example of RPC. So, you just effectively, you're invoking a method in a separate process and treating it as if you're in the same process. So get user by full name. And then you have the idea of document-oriented, which basically is a bit like working in a 50s enterprise, in a 50s organization. So people can get the idea when I talk about that. But as an example, if you think about booking holiday before we had email or corporate intranets or any of these kinds of things, how would you book holiday? Well, you'd go to a cupboard, you'd pick out a holiday form, you'd fill in the holiday form, you'd stick it in an envelope, you put it in your outbox, and then Dave or Pete or someone, probably in one of those kind of fawn coats would sort of turn up with a flat cap and take stuff from your outbox. They'd go to HR. HR would get it in their inbox. They'd look at the holiday. They'd say, yes, approved, stamp it, send it back, and eventually you get it back in your inbox and see whether your holiday's been approved or not. That's basically messages, as far as I can make out. That's how message buses work. Interesting characteristic of messaging, of course, is that it's asynchronous. And much like the 50s enterprise was asynchronous, because when you're you fill in your form, you put it in your outbox, you don't suddenly block waiting until it comes back into your inbox again. You kind of you actually get on and do stuff in the meantime until the message comes back. That's basically document oriented. Then about, I guess it was, well, 2008, there was a fantastic presentation, and it's online, you can get hold of it, by a guy called Leonard Richardson. It was called Justice Will Take Us a Million Intricate Moves. And he was talking about the idea of using resource-oriented architectures, or effectively using the web and the RESTful style to do integration. The reason it's called a million intricate moves is basically there's a million things, there's a million integration problems out there, and we're going to have to solve each one individually. But yeah, justice will take us a million intricate moves. And basically in that presentation he talks about what is it about big organizations where we think like that we have to build it all ourselves and solve all the problems ourselves. You know, we look outside and there's this giant kind of distributed system, the most successful distributed system on the planet, the World Wide Web, built on top of the internet. It seems to be doing okay. You know, as I say, it hasn't gone anywhere. It's only getting it's only getting bigger, you know, more exciting, more technologies that we can use. But for some reason, inside our own organizations, we have to go off and buy a massive set of Oracle tools or a massive set of IBM tools, or we'll build it ourselves. Yeah, which tend to be black boxes, they're not transparent, they tend to cost lots of money, they tend to be difficult to integrate with, they tend to degrade over time as you customize them, these kinds of things. What is it about us that doesn't allow us to actually just use the web to do this stuff? That's a colleague of ours, former colleague rather, and a co-author of REST in Practice. He puts it, be of the web, not behind the web. So bring the web inside your organization. Use all the tooling and techniques that we use to program externally to actually program our systems internally as well. So this is things like resource representations, integrating via RESTful architectural style. Bring that stuff inside and it will have a lot of benefits. And there's a sort of very quick example of that. Here are sort of, you know, we talked about ports and adapters. Well, maybe one of the ports is sort of a RESTful a resource representation that is exposed on a URI. So in this case, artists / some kind of GUID, and which you can get hold of by using one of the limited number of HTTP verbs. So get. And then you get back a representation, which is in this case JSON. And the cool thing in the case of this JSON is that it's got hypermedia controls. This is the hypermedia as the engine of applications state constraint from Roy Fielding's RESTful paper, or REST paper. Basically, what that means is use links. So it turns out you can link between stuff on the web, and it's become very successful. You can look at things and think, oh, I want to go, I can see a link on a page, I can click it, and it'll take me somewhere else. All right, we can use these techniques actually to integrate software within our organizations as well, and use hypermedia controls actually to allow the services that we produce to decouple themselves more from the clients using those services. So the next characteristic is the idea of small with a single responsibility. So there's, you know, people, who's heard of the single responsibility principle in the room? Solid. What about integration? Interface segregation, that's the one that I don't get. But yeah, single responsibility principle. So I always thought that the statement of the single responsibility principle was, you know, you should have, so each object at the level of object orientation should have a single responsibility, should do a single thing. Interestingly, that wasn't the original formulation. The original formulation is should have a single reason to change, which is similar but not exactly the same. But I've kind of got this idea about architecture and about kind of building out microservice style distributed systems, that the single responsibility principle is key and actually sort of lets us think about what size these services should be. And the reason is, I think, well, we've got this sort of single service here with a database in this, you know, bounded context. But actually, from our example with the event queue and the competing consumers and things, we had 3 services, we had 2 databases. As you drive down, you know, into one of those services, they're probably composed of objects, or we are in Shoreditch, there's probably a huge number of Clojure programmers in the room, because, you know, that's the kind of obviously hipster thing to do at the moment. I personally, as I say, prefer things like, you know, COBOL, that kind of stuff. But you know, so as you dig down, as you drive down into one of these services, they're composed of objects. And as you drive down into the object, my theory, and this is my conjecture, is that these objects should be no bigger than my head. By which I mean, when I hold my head up to a screen, They shouldn't be any bigger than that. That's the lines of code on a screen. Yeah, but that's okay, because it's massive, my head. It's quite empty, just so you know, quite empty. And I can tell you it's massive because this is really going to have tram lines down the side of my head from this microphone later. But there's actually a sort of a serious point here. When I say, that's actually not a bad kind of guideline. Objects should be pretty small in terms of the screen full of codes and so on. But also, I should be able to comprehend everything that an object does in its entirety. Right? I shouldn't have to keep like flipping back and forth between different things that it does. I should be able to focus and understand in its entirety the point of that particular object, the function of it. So it should fit in my head, effectively. Conceptually, it should fit in my head. And this is kind of interesting here with memory. I'm getting older now, turns out. And it turns out, as I get older, I keep forgetting what other parts of systems are doing. I'm like, what the hell does this do again? But you should be able to look at something and you should be able to understand exactly what it does. It should be able to fit in your head. And my theory is that as you scale up, that's true at the level of object, as you chunk up through the different technical levels of abstraction within your system, that should be the case all the way. So at the level of the object, it should be the case. At the level of a microservice, you should be able to understand exactly what it does. In the example, we had a competing consumer, we had an event queue, we had a user service, which was the source of truth for users. Right? Each of those things has very distinct responsibilities, a distinct reason to change, and you can understand each one of them in its entirety without having to conceptually make a leap anywhere else. And similarly, as you chunk up to the level of a bounded context, it should have a single responsibility, should do a particular thing. In the example, it was user management. It's the source of truth for users. And then as you chunk up to systems of systems, they should also fit in our heads. So as we chunk up the level, the technical domain level, each domain should be small enough you should be able to understand it conceptually at every single point. And one of the big problems I think we see in software is that we mix different levels of abstraction. We end up with different levels, and we kind of have this cognitive overhead, this cognitive load that comes from trying to sort of translate between different levels of abstraction. If you try and keep things separate into these sort of very, very small, very distinct components with single responsibilities, I think it should kind of help. So I'm going to take a sort of jump sideways into more organizational concerns here. So one of the organizational characteristics, and I appreciate that we're all on these hard wooden chairs, so bear with me. It's this idea of using product lines and not organizing around functional silo. So, traditionally, big organizations or any organization probably looked a bit like this. You'd have different functional silos. You'd probably have a project management office. You'd probably have some operations people, some testers, some developers, all in their operational groups. And when we wanted to build something, we'd start a project, and we'd have like maybe 3 of these developers over here. From the development group would be assigned to the project for a bit. If you're lucky, they'd be on 100% time. They might be, in the worst cases, having 30% of their time on one particular project, 30% on another project, and 40% on a different project, and that introduces all kinds of craziness. And then on the other side, you have the business, right? So you have these functional silos and the business, and of course that's actually what it looks like, because generally developers aren't even allowed to talk to the business. You have this yawning crevasse of doom between your IT organization and your business organization. So one of the interesting things about building systems out of these business capabilities that are communicating with one another is you can kind of break down some of these functional silos. And I mentioned, sort of XP and Agile at the start. A core part of building systems in most of the Agile methodologies is you have cross-functional teams. So you have teams that are composed of all the different roles, including roles from the business, so including product owners or maybe product managers from the business, all inside a single team building out software. Now, ThoughtWorks, we're a consultancy organization. Generally, what we do is spin up project teams. We'll have a team, but it's for a particular project, runs for the lifetime of the project, and then stops. And that's kind of not necessarily the best way of organizing yourselves if you're not a consultancy. That's kind of what we have to do because we're a consultancy. But if you're not in a consultancy, that's a particularly ineffective way of organizing your teams. And so one of the proposals, or this key characteristic rather, is that you should organize these cross-functional teams around these products, around product lines, around long-lived services or long-lived product lines. Maybe they're groups of services. And this is effectively around these business capabilities. So there's a kind of interesting thing that happened some years ago. is a guy called Melvin Conway, and he came up with this thing that's now known as Conway's law. So just hands up, anyone heard of Conway's law in the room? We've got quite a few people. So simply stated, Conway's law tells us that the way we organize our teams, our software ends up looking like that, effectively, right? That's pretty much a simple statement of Conway's law. Specifically, organizations which design systems are constrained to produce designs which are copies of the communication structures of those organizations. It's just a fact. It's just how communication works when you've got large groups of people. We end up mirroring the design of our software ends up mirroring how we put our teams together. So an example of this, and this is the kind of canonical, I guess, example, is if you've got a group of DBAs, you've got a group of middleware people, and you've got a group of UX people or front-end people, you end up with some front-end, some middleware, also server-side stuff, and some databases. You end up with a kind of three-tier system. Dan North talks about this. If you ask 7 people to write a compiler, you end up with a 7-pass compiler, which is a kind of nice way of looking at it. This was verified by Microsoft some years later. I think when Melvin Conway originally submitted his paper to, I think it was Harvard, HBR again, they rejected it and said, no, this is nonsense. But then Microsoft did a lot of research. They actually looked at how the Windows operating system at the time, I think it was 95, was put together, and they looked at their team structures and they could see distinct similarities. They went on to look at the way Office was put together, and the same sort of thing happened. So they eventually resubmitted this paper, and HBR did another study, and they've kind of confirmed that this is something that kind of happens. Well, the cool thing is you can actually use this to your advantage rather than it being a kind of constricting factor. You can actually say, if we've got this kind of enterprise, this evolutionary architecture, this kind of town plan composed of these zones which represent these distinct sort of business capabilities bound in context, then we can actually organize teams around these things, and that actually reinforces the kind of architectural separation, or the separation between these different bounded contexts. So we actually use Conway's law to our advantage. So you can organize these teams around systems. Famously, you've got Amazon. Amazon popularized this with a 2-pizza team. So you should have a team no bigger than can be fed by 2 pizzas. And they're responsible for every aspect of their team. So including, in some cases, things like profit and loss, that they're their own profit and loss centers, and so on. Similarly with Netflix, they're organized completely around these services that they go out and build. And there's another client I've been working at pretty much over the past year that has reorganized their entire department from functional silos into being organized around distinct product lines where they're sort of long-lived teams building out products over their lifetime. So this is an example from another client some time back, where this is kind of the town plan, the sort of evolutionary architecture map of effectively what is a sort of a retail bank in a box. If you were to build a retail bank, you'd need a bunch of this stuff. It's not complete, but you've got things like user management, transactions and account management, rules around. In this case, it's slightly different. There's kind of a whole set of rules engines and things, reporting, access and entitlements, and then distinct website call centers analytics. And so what we decided to do is break up what could have been a very, very large program team into a much smaller set of teams, each focused around these individual core capabilities, And kind of, this looked a bit like this. We had a number of different work streams. The pink cards on this represent a single capability. There's some writing. That's the number of story points. And then we had a number of pairs who were working in parallel to build out these capabilities, which were entirely separate from one another. So this is, again, using the idea of Conway's law to enforce the separation of your sort of town plan. The interesting aspect about this is that this also increases the surface area that you have to work with. So when you're looking to scale building out software products, often you get to a point where you can't scale because you end up treading on each other's toes. You're working in the same areas of the code base, things like kind of merge hell happen and all this kind of stuff. But if you've got distinct separate services, distinct separate teams working on them, it increases the surface area and allows you to work on these individual components in isolation. So the next thing is this idea of decentralized governance. I think it's safe to say that this idea of the kind of microservice style is pretty much developer-led. It's a developer-led approach, by which I mean a bit like XP. It's kind of been a bottom-up approach to building out systems of systems. So when I say decentralized governance, it's probably no surprise that these sort of developers would prefer to be responsible for their own destinies rather than anything else. And one aspect of this is the ability to not have to choose the same tool despite the circumstances you find yourself in. And this is one of the kind of core things around centralized governance. We'll put in place some kind of model which says thou shalt only use this programming language, this enterprise architecture approves the group approved set of tooling, and now shall go off and build your software using it. I mean, this actually does kind of introduce kind of problems because, you know, I think we could probably all agree it's better to use the right tool for the job. I mean, I'd hate to think what would happen if Facebook tried to model everything in a document store, say, or you know, they need to, as organisations, we need to allow. As we drive responsibility downwards, our teams to be able to choose the right software to solve the right problems. An example of this is from a client last year. We had 3 distinct sets of services. We had products in this case. So we had a product that was one type of insurance product. We had another capability which was effectively integration with our enterprise reporting tooling, so talking out to our data warehouse. And we had another product which was kind of our real-time analytics, which told us how much money we were making. And in this case, what we decided to do is we had 2 of these products that were built out using C#, and one of these products was built out using Node because we were able to take advantage of the fact that we could go quite a lot faster actually with Node. We found ourselves going quite a lot faster with Node than with C#. So we had distinct technology choices dependent on the actual factors involved in those capabilities. This is another example from the same client where we were actually using a document store in one area and then we had 2 SQL Server databases that we needed to integrate with. But the key thing is we were separated from these. We had separate products, separate capabilities, so we could actually choose the fact that our domain was well suited to storing, you know, it was effectively, we were creating big insurance forms, application forms. Turns out forms look quite, you know, they're kind of document-centric, and document stores are quite a good fit for storing those rather than relational databases. Whereas, you know, if we had to integrate with an enterprise data warehouse, which was in SQL Server in a classic kind of star schema. And this is another kind of aspect of this decentralized governance, and why I talked about replaceable at the start. Dan North talks about replaceable component architectures. He doesn't really like the term microservices. He feels that replaceable component architectures talk more to this idea that these things should be really small and you can throw them away rather than maintain them over a period of time. They should be small enough that you can actually get rid of them rather than maintain them. And why might you want to do that? So an example, you know, again, we've got kind of MongoDB, got a document store, maybe some SQL Server stores. It might be that part of our reporting is better suited to a graph model. We might want to be doing something that's much better suited to a graph model than to a relational database, so we might over time want to migrate away from SQL Server to Neo4j, say, because our problem was better handled with a graph database. So this idea of decentralized governance doesn't mean there's not any sort of governance. In a lot of the organizations, things like Netflix and Twitter, the Twitters and that kind of thing, there is governance, but it's in this area of sharing tools rather than enforcing standards. So rather than thou shalt, it's let's create tools that make it, harvest tools that make it easy for people to do the right thing over a period of time. Which is in distinct contrast to, this is the WS star specification, which anyone's ever had to spend some time understanding the WS star specification is kind of terrifying. So rather than coming up with this really heavyweight, thou shalt do this, thou shalt follow these specifications, thou shalt use WS choreography in order to choreograph your systems, we use things like, you know, open source tooling harvested from the teams themselves. So, you know, with Netflix is a great example. If you haven't seen the Netflix open source site, that's on GitHub, go and have a look. They've got so much cool tooling there. It's just unbelievable the number of tools that they've produced for themselves that they've now open sourced. This idea of sharing useful tools that you've harvested, and you know, they have this rule where, you know, so they've got one of these tools is a Cassandra client. That allows them, it's got some interesting monitoring stuff around talking with Cassandra and things. They kind of say you should use this because we've put some work into doing it, and it's quite robust and scalable. You get a bunch of stuff for free. But what they don't do is say you have to use it. They don't even say you have to use Cassandra. You know, they actually say you can choose the right tool, but if it looks like a fit for this particular technology, you probably want to be using this stuff. And they trust the people that that are working for them at Netflix to get on and do the best by the organization. So, decentralized data management. This is another example. Well, this is a slightly different view on the example I gave earlier, where each of the colors in this represent a different type of data. And this is one of the problems we often see, is where you get data kind of smeared out all over, different types of data in sort of in these stovepipes smeared out all over organizations. And often in kind of monoliths, as I sort of said earlier with Netflix, with monoliths you have lots of different types of data in the same place. But then when you move to this microservice model, you tend to sort of start splitting out that data, so each individual piece of that data is owned by its separate kind of microservice. And as I said, Netflix have taken this to the nth degree, where they have specific, it's down to the level of the table. I'm not suggesting that that's going to be right for everyone. That's right for their use case, where their use case is we want to be able to go as fast as possible, and we're willing to accept the overhead of managing all this stuff, of managing all this additional operational complexity. That's probably not appropriate to a lot of organizations, but the key concept is you have these services that own their own data, generally is. The key thing that often comes up in this kind of, when you start talking about denormalizing data across multiple different services, is what happens about transactions. How do you manage the fact that you might need to keep one piece of data consistent with another piece of data? And the actual, and this might sound like a bit of a kind of a silly answer, but actually transactions kind of really, well, they've always been really, really hard. If everything's in the same database, you still have a transaction. It's just that the database is managing the transaction. If you've got that data smeared out across multiple different data stores, how do you look at managing consistent reads and writes across those different data stores? One option is this idea of distributed transactions, and you can use things like Zookeeper to allow you to have like global locks in your distributed system, so that you lock an object in Zookeeper or in a central repo, and whilst that lock is held, you can make writes across multiple data sources. Frankly, I think that's bloody awful. Not to put too fine a point on it, and that you should do everything possible to minimize the use of distributed transactions, especially when you're looking at building distributed systems. But there must be this kind of alternative. And what is the alternative? Well, Jim Weber and Ian Robinson talk about the idea of favoring service choreography over service orchestration. So the orchestration model is very much distributed transaction. You have the conductor at the front with an orchestra, and the conductor tells everything what to do. I need to perform an operation across multiple systems, so thou shalt do this, thou shalt do that, thou shalt do this, thou shalt do that. That's the kind of distributed transaction model, the kind of orchestration model that we're familiar with in lots of organizations with big sort of business processes, modeling tools and things like that. Or business process orchestration tools, rather. In the microservice world, the kind of idea is to favor choreography, which is more about the idea of kind of principal dancers being taught or being instructed in a piece of music, in a dance before they go on stage, and then when they go on stage, they're on their own. There's no central person there saying, right, you raise your left arm now, you do a high kick. I'm not very good with dance terms. I don't look like a dancer, right? But that's the basic idea. You set up the initial conditions for transactions to proceed, for local transactions to proceed, and then over time, the individual systems just kind of tick along, purring in the background, processing transactions as they go. So an example of that might be you have a business process which traditionally would be orchestrated by some central piece. Do this, do this, do this, do this. Rather than have that, you have the individual pieces are polling each other or are using some kind of asynchronous method. So they might be using events and passing events along so that each individual component can do its own piece of work and then pass on an event potentially into another chain. And because this has like sort of important implications with respect to cap theorem. So we're talking about the idea of only being able to have two of consistency, availability, and network partition tolerance. Now, this is a kind of key concept. If you're building a distributed system, you can only have two out of these three. And because we need to be partition tolerant, you end up having to choose between consistency and availability when you're building systems. I think it's interesting because you talk to business people and you talk to senior technical people and they favor consistency above all else. effectively, generally. Oh, we must be able to have consistent reads after a write. This has to happen across all of our systems. Actually, if you talk to business people, they're often quite willing to trade off consistency in short time frames for availability. And it's not something we often do. It's not something we often have the conversation around. It's kind of interesting. And if you kind of have this idea of can you beat the cap theory? We can have all three. There's this fantastic blog or fantastic article called "Beating the Cap Theorem Checklist." If you can't read that, there's some things on here. It's basically a dismissal of most of the reasons that people have come up with where you think you can actually beat the cap theorem. But certainly when you're building distributed systems, how you keep data consistent or not, or data available or not, is something that you have to think about. The cool thing is, of course, you can actually decompose the problem more. You can divide and conquer, and rather than say the system as a whole is either CP or AP, you can say these parts of it are CP, these parts of it are AP. An example of that might be something like billing on a website. So we might say the product catalog is going to be AP. We want to be able to be highly available, so we're going to accept stale reads on the product catalog. But when we want to charge someone's credit card, we're going to say it's CP, it's consistent. We want to make sure that we're going to consistently write that data and be able to read it. So you can choose, is what I'm saying. If you separate these systems out, you can actually choose different characteristics for different parts of these systems. So the next thing is the idea of building, deploying, and scaling automatically. So what's the difference, effectively, between building and deploying a big monolithic application and lots of smaller ones? Well, so in ThoughtWorks, it's probably about 8 months ago now, I sent we had like an internal survey. We kind of basically asked a group of projects in the UK, are you building systems that look a bit like this, look a bit like microservices? And of the respondents, I think we had 10 out of 16, we had 16 respondents across the project portfolio. 10 out of those said they were building distributed systems, effectively. And I asked a few other questions as part of this survey. And one of those questions was, are you using automated provisioning and virtualization? And of those 10 that said they were building distributed systems, 80% said that they are using infrastructure automation techniques and virtualization. And for me, that's the kind of core thing. This is one of the key enabling factors that allows us now to build these distributed systems, is that we can use virtualization and infrastructure automation to take the weight off the operational complexity inherent in having many more systems. So if we're building these things that are independently scalable, deployable, changeable, replaceable, and independently you can apply different AP or CP characteristics to, we want to be able to build them, deploy them, and scale them automatically. And automatically is the kind of is the key point here. We need to be doing this automatically, and in fact, we need to automate all the things. That's what we need to do, because in an ideal world, rather than deploy months or weeks or days, we want to be able to deploy push button. We want to be able to deploy in a matter of hours. We want to be able to deploy on demand. That's the key thing. So if you look at an organization like Netflix, they'll push out tens and tens and tens of new versions of production code every day. Each of the individual services is independently deployable. They will push these out kind of many times a day. This is a basic build pipeline. The key thing when you're building systems of systems is you want to be able to lean on this tooling to allow you to get confidence that when you're pushing code through into production, it's reliable and it's going to behave as you expect. And the key with the build pipeline is you're going to be pushing code through many different environments. And as you push them through more environments, you get more confidence. It's probably this way. I'm following my slide, but it's backwards, isn't it? So you get more confident as you go forwards because you're running more and different automated testing, including these days automated penetration testing, automated accessibility testing, automated performance testing every single time you make a change. But you also want this staged pipeline because you want fast feedback as early as possible if something's broken. So how do you do that? The key thing here is using things like, now this is both a chef and a puppet. And I've used that joke a lot, but it's pretty, woo. you can use tooling like Puppet, you can use tooling like Chef to do automated provisioning, automated configuration management of your software. You can use tooling to do automated provisioning, so all of the AWS tooling. You can use tools like Fabric that allow you to talk to anything that you can talk to via SSH. Even Microsoft is getting involved in this now. I think they've got a lightweight OS that they're starting to push, which is much easier to automate deployment of. And then you use tools, or you use techniques like Phoenix infrastructure. So this is the idea that you don't have long-lived infrastructure anymore. You don't allow your servers to go on for days and weeks and months, or years. What you do is you actually deploy, rather than deploy software into an application server, say on a long-lived server. What you do is you start up an entire new server and delete an old one instead. So this idea of rising from the ashes, you have these kind of Phoenix-like pieces of infrastructure that you can just delete, you just terminate over time. And in fact, I think The Guardian have got their analytics platform. The way they deploy their analytics platform, they've got like 5 instances running in an autoscale group on AWS. They say, okay, scale up to 10, so 5 new boxes will start, software will be installed on them, and then they say to scale back down to 5, and the oldest 5 will just be deleted. And that's a deployment for the analytics infrastructure at The Guardian. It's kind of I guess there's kind of interesting stuff. There are second-order factors or second-order effects starting to occur when you start thinking about hardware as ephemeral and programmable. So finally, you'll be pleased to know, we're going to talk about being designed for failure. I mean, the thing is, if you've got a monolith, it's in one of 2 states, right? It's going to either be up or down. That's effectively the 2 states that a monolith can be, or it could be maybe a bit slow. But it's kind of easy to reason about a monolith. It's easy to know whether it's up, whether it's down, or whether it's slow. Now, if you've got a distributed system, if you've got a directed graph, effectively, of services that are communicating with one another, either asynchronously or synchronously, if one of these services goes away, how do you know whether that system as a whole is up or down? Or if you get a slowdown in that distributed system, how do you actually know where that slowdown is occurring? And this is kind of a core point here, that you really need to get serious about putting a load of tooling around understanding your infrastructure, understanding what these services are up to. But fortunately, that's okay. Martin Fowler talks about pushing accidental complexity into infrastructure. So in the past, you have the essential complexity of the business problem you're trying to solve, and then the accidental complexity is the cruft around it, the kind of spaghetti that ends up growing out around it, that isn't related to the specific business problem. In this case, what happens is you can get really, really focused, small pieces of code which focus on essential complexity, which are the microservices, but then that accidental complexity pushes out into the communication pathways between those microservices. Here's an example from Mike Nygaard. This is a great quote. He wrote Release It, which is a great book, by the way. Go out and read that if you haven't. Every socket, process, pipe, or remote procedure call can and will hang, even database calls. Now, this is the same for a monolith. If you have a monolith talking to a database, this is as true for that as it is for distributed system. But if you've got a distributed system, it's going to happen more often. It's going to happen more. It's going to be more likely. So you end up, you can use a whole bunch of tools, things like Graphite, which you can poke performance metrics into. You can do log aggregation using tools like Logstash or Kibana. These kind of tooling to allow you to make sense of what's going on in your system over time. This is again back to the Netflix open source page. Can you tell I'm a big fan of this? Not sure. But there's a tool they've got called Hystrix, which is the implementation of the circuit breaker pattern. And this is a pretty cool pattern, the circuit breaker. It's where if you've got 2 systems that are communicating, if I'm talking to another system and that system either starts to slow down or I can't talk to it anymore, the network partitions say, then with the circuit breaker pattern, you actually detect that and you break the circuit and say, okay, well, if I can't communicate with that external system anymore, I'll maybe do an incremental back off. I'll try once every 1 second, then 3 seconds, then 5 seconds, and then once that service comes back, I'll trip the circuit back, I'll close the circuit, and we'll go back into normal production mode. And this is there's tooling out there to allow you to do this automatically. Things like Drop Wizard have a whole bunch of metric and health checks in. This is the output from Hystrix. So Hystrix endpoint will allow you to see all this sort of information around throughput for a particular circuit, whether it's up, well, whether it's open or closed, the different latencies involved in network calls and things. There's also another tool which is pretty cool from Twitter called Zipkin, and Zipkin effectively gives you like the network pane on your Firefox or Chrome dev tools. You know, the network pane which says this HTTP call took this length of time. What Zipkin does is it effectively uses a correlation ID that traces through all your services, so you can actually look at in a network pane-like interface how long it takes for each part of your for each call to propagate throughout all the services in your distributed system. So this is an example of what this sort of thing might look like. You know, you kind of put all these big pieces in place, and you end up with a lot more safety around whether your system is operating in a good or known state. So I'm going to finish off with this idea of standing on the shoulders of giants. So, you know, I think I said at the start, this is like the London School of Architecture, or Evolutionary Architecture or Design. Really, it's not. Really, this goes back to these guys. This is Ken Thompson, Dennis Ritchie, back in 1969. And that's for those of you who were around back then, that's not me. That was 6 years before I was born. 5 years before I was born, rather. That's a PDP-11, and the PDP-7 was the box that Unix was invented on, or to be the operating system of. And a lot of this stuff actually goes back to Unix and goes back to something called the Unix philosophy. And this is kind of best expressed in Lyon's commentary on Unix, second edition, slip of the tongue. I mean, he says. Write programs, he's talking about when the pipe and filter metaphor was first used, or first became applied in Unix, right? So the pipe and filter metaphor being everything's basically a text stream. You know, you have a file as the universal metaphor, and you're able to pipe text streams between different processes and filter them and so on. So he says, write programs that do one thing and do it well. Write programs to work together, write programs that handle text streams, because that is a universal interface. So this is going back quite a long time now. I think this is 73 this book was out, and this book, that quote basically says, write programs that follow the single responsibility principle, write programs that work together at a distance, write programs that handle text streams, because that is a universal interface. The universal interface we've been talking about in terms of things like HTTP and REST. They kind of did all this stuff a long time ago. Goes on to say, with pipes, many programs could work together, and they could work together at a distance. And I think if you kind of substitute HTTP in there for pipes, you get kind of pretty much what we've been talking about. Lots of small programs that are talking through a clear, transparent interface to one another that are decoupled with single responsibilities. So I did have some references. So these books, if you haven't come across these books, I highly recommend them. So the first one, Release It, Mike Nygaard. That's fantastic. It's about how you build reliable systems. It's a really good read. It's kind of a set of stories, effectively, about things that went wrong in his career and how he kind of addressed them, and patterns. So Circuit Breaker is a pattern from that book. There's enterprise integration patterns. There's a lot of the messaging stuff is in there. Domain-driven design, continuous delivery. So everything you need to know about blue-green deploys, A/B testing is in continuous delivery. REST in practice, if you want to learn more about how you can use REST to create application protocols, and then the art of Unix programming. I kind of you'll get all these slides. So I put together a handy checklist for how you build systems over time, how you build these kind of systems. So this is my checklist. You got 17 or so different rules. Rule of modularity, simple parts connected by clean interfaces. Clarity is better than cleverness. Things like simplicity, design for simplicity, add complexity only when you must. Where's that one? Least surprise, always do the least surprising thing. I think that's a kind of nice one. Some of the more observant or grey-bearded folk in the room might have realised that actually those are the 17 rules of Unix programming. So as I say, pretty much standing on the shoulders of giants. All I've said today goes back to Unix. So, I guess in summary, we've had, and I'm not claiming. We'll come on to this. I'm not claiming that this is the way everyone should be building systems these days. But we've had some success, and there are a group of people. There's a kind of community growing around this that are building systems using these techniques, small services cooperating, talking to one another using simple, clean interfaces. And what we found is they're quite cheap to replace. They're kind of easy to scale using the kind of infrastructure automation and techniques, and that you can continuously deploy them. And they allow you to basically go fast and adapt to changes in your environment. Adrian Cockcroft, who's the former director of cloud engineering at Netflix, we were chatting. I'm a terrible name dropper. We were chatting a few maybe last week. His response when people ask him about why they built the systems they do, and why they built the system the way they do, is because it allows them to go as fast as possible. It allows them to be as agile, as maneuverable as possible as a business. So finally, the last slide. The 16th rule of Unix programming is the rule of diversity. So distrust all claims for one true way. Don't take my word for any of this. Maybe try it. Maybe try it on something that's not necessarily too risky for your organizations. But it is a really exciting and interesting time to be involved, I think, in building software using the microservice architectural style. So thank you very much. That's me.